Hi everyone. In this video what I'm going to do is talk about the calculation part for the resonance of open and closed pipes. So in the previous video I showed you and derived out the standing wave patterns in both open and closed pipes. So now that we kind of see where the relationships come from, I'm going to show you how to use those relationships via calculations and go through different ways the material can be presented to make the calculations. So I'm starting here on our open pipe harmonic series. So we saw that with open pipes that the harmonic series actually goes in halves, which is where the factor of 2 comes from in this equation like this. So just to kind of introduce what's going on here, F stands for frequency. So if I want to know what the sound is making or sound like with the pipe, that's the frequency measured in hertz right there. L stands for the length of the pipe. Make sure it's in meters. A lot of times the values are in centimeters, so you need to convert that. V is now the speed of the wave in air. So as before with standing waves and strings, it was the string wave. Now it's the air wave, or the speed of sound in air. And N comes down to the harmonic number. So when it comes down to open pipes, any harmonic is, any integer is acceptable. So 1, 2, 3, etc. like that. So let's solve some questions. So here are some of the ways you can present the information. So in this question, you can see here that we have 2 different standing waves, and in both of the questions it's asking for the wavelength. When it comes to figuring, so the wavelength is going to be 2L over N, so I got that from our relationships from before. So we need to know the length and the harmonic number. So in this question they give you a visual. For open pipes, to find the harmonic number, count the nodes. So 1, 2, 3. Try to make them a little larger here. But if you notice we have 3 nodes, so N is going to equal to 3.
Natalia DePonte, please come to the main office. Natalia DePonte, please come to the main office.
I love announcements. Okay. So there's 3 nodes. So if you count the nodes, you can get the harmonic number. So really quickly, you notice 1, 2, 3, 4. The harmonic number for this one is 4. So there you go with that. After we get the harmonic number, we need the length. But like I said, that's in centimeters, so we need to convert to meters. So the wavelength will be 2 times 0.63 for meters divided by 3. Sorry about the messiness here. My calculator's right here. 2 times 0.63 divided by 3 gives us 0.042. meters for problem A. So what does this represent? It represents the fact that the wavelength, the wave that's trapped in here, is 0.42 meters long. So from here to here, one full wavelength. If I cut it off, that's a wavelength. 0.42. Notice the length of the pipe is 63, so it's about 2/3 or 2/4 like that. So that's what we're measuring here, the wavelength, not the length. So the length would be L, sorry for the messiness, but the L is the length here. The wavelength is just one waveform that fits in the pipe like that. So let's see if I can do this. Just erasing my annotation. There we go. So you can physically do that. So notice, I'll skip this one, but you could do the same thing, 2L over N, with a very similar calculation. They don't have to give you a visual. They could give you just a number. So you're looking for harmonic number. So this one literally says N equals 1. Therefore, N is going to equal to 1. This one says N equals to 5. So you don't have to have a visual all the time with our harmonic series, but it's good to identify this. This is a great AP question, is just being able to recognize what standing wave number you're working with. But sometimes it's not just given as a visual, as you can see here. So since this is just a repeat of what I just solved, you're using the same equation for all of these cases. So I'll just leave it here. And if you notice that, in all these cases it's in centimeters, so you need to convert into meters, except for this one, of course. So just pay attention, that's all, when it comes down to that. So here's another one where they give you a diagram, you have to figure things out. So it wants the frequency. So in a harmonic series of open pipes, so the key word is open here, so you have to pay attention to that too, because that tells you what equation to use. For open pipes, it's NV over 2L. For closed pipes, it's a different equation, so you do need that key word. And it shows us the resonance to the right. It gives us a length of 0.0638 because we need to be in meters. The velocity is 345 meters per second. And N comes from the picture, 1, 2, 3. Harmonic 3. Now that we have all the information, we can go ahead and plug in our numbers. So F is going to be the harmonic number, which is 3 times 345 meters per second divided by 2 L. So let's go ahead and solve that out. So 3 times 345 divided by 2 divided by 0.638. The value you get is 811.13 hertz. Like that. And that is our answer for that. So you could flip this around and solve for length, velocity, harmonic number, so it does not always has to be in this case. Let's try another one. Well, maybe not. So anyway, this is a harmonic for the third harmonic, by the way. Notice that n is equal to 3. So if I wanted to find the first harmonic, just out of curiosity, Fn equals F1 times n. So if I know the frequency of the third harmonic, I can find the first. So I'm going to go ahead and solve that. This is a completely unrelated question. But I know that 811.13 hertz is going to equal to the first harmonic times 3. So if I divide both sides by 3 to solve for F1, just because I ran out of space, I'm just going to write it right here. The first harmonic is 270.3, and then on my calculator I'm just rounding 8. There you go. So those are just different ways to look at these problems. So I'm going to go ahead and skip over to the calculations. So this is, we went through this in the other video. So this is just a nice visual too. I know I didn't have it in the other video, but this is what the standing waves actually look like given their wave patterns, because it's kind of hard to visualize some of these things. But these are the waves that get trapped in there for the closed pipe specifically. And recall that the closed pipe, your harmonics are odd. So the first order harmonic is 1, your second order is 3, your third order is 5. So we're going in orders of odd numbers, so just know that. Because of that, we have different equations. There's a factor of 4, so we go up in quarters instead of halves. And that changes our calculations and the equation for this. So notice you have some similarities. The biggest difference is the factor of 4 and the odd numbers right here. So notice that you do have to pay attention to what system you're dealing with, and then you have to make sure that you apply the right relationship. So V is the velocity in air, L is the length of the pipe, frequency is what it sounds like in hertz, harmonic number has to be odd. So let's do a few problems to kind of look at this. So when it comes to determining the wavelength is going to be, oops, let's see if I can fix my pen here. Sorry about that. Okay. Okay. So the wavelength. My pen doesn't want to work. Let's see. Discard. Let's try again. The wavelength. Oh boy. we'll get this, don't worry. The wavelength, there you go, is 4L over N. But when it comes down to figuring out what harmonic number we have, the best way is to count the nodes and then get the order. So one node is the first order, 2 nodes is the second order, etc. So notice if I count nodes, 1, 2, 3, 3 nodes equals third order, which means N is going to be 1, 3, 5. Okay? Not, it's 5 because we're going in orders of odd numbers, and the third one is 5, 1, 3, 5. So that's a little different according to the diagram that we have up here. And then we apply the equation very much the same way. 4 times the length, which is 0.35 because of the centimeter part, divided by 5. This is for part A. I just moved it down here. The wavelength is 0.28 meters long. So let's take a look. I always like to check too. So if you notice, the wavelength measurement is from here to here. Remember, we need one full up and one full down and back to the start. So this is one full wavelength right there. And 0.28 makes sense because the total length is 35. So the L for 35 is here. Good. So that's where it is. And if you notice that we basically have one full wave plus a quarter. So we have 5 quarters of a wave. I'm sorry, 4 quarters of a wave in one pipe, and that makes sense. So because this one's very similar, I'll just do the harmonic number. So 1, 2, 3, 4. 4 nodes equals 4 orders. So 1, 3, 5, 7. 7 is the 4th order, so N equals 7 here. So that'll be the hardest part. Now when it comes to word problems in standing waves, they'll give you the value. So first harmonic, N is equal to 1. Fifth harmonic is the 5th harmonic, okay? They're not going to go in orders, okay, because it's too confusing without the visual. So they're just going to tell you straight up if it's a word problem. If it's a visual, you have to do it differently, but if it's a word problem, they're going to give you the N number. So here are 2 other examples. Let's go through them. Yep. So now in this question, we're going to look at the frequency. So now we're going to use this relationship, NV over 4L. So let's go through the problem. Find the frequency of the first harmonic, so N is going to equal to 1. First harmonic. Air column, L is going to be 0.172. And the speed of the sound, V, is 340. So now we can calculate F. F is going to be 1 times 340, that's the speed, times harmonic number, divided by 4, and then the length 172 meters. 340 divided by 4 by 0.172. Our value is 494.19 hertz. That is the first harmonic played by that instrument, by the test tubes, I guess, like that. So that's how you can solve that question. And then in this question, I have a closed-end organ pipe. Makes a mix of sounds, the 3rd and the 5th. So like I said, these are actually N equals 3, N equals 5. They told us the 3rd and the 5th are 111 hertz, and then 1833. and this is the frequency of the third. So notice that's notation. Sorry, let me go back here. Nope, I can't erase it. F5 just means the fifth harmonic frequency, and this is the third harmonic frequency. So I'm not doing any multiplication, this is notation. What's the frequency of the first harmonic played? So actually, the best way is to do the equation we've used before, like this. Now, they actually gave us a lot more information than we needed. Quite technically, I only need to do this once, so I'll do the first set. So we know that at the third, that's our fundamental. I'm sorry, that's our frequency. So notice I can solve for this. 111, 1,100 divided by 3, 360, I'm going to round 6.67 hertz. Now, like I said, they give you way more information. Ideally, we can do the same thing again with the other one. Let's just do it for completion. You don't need to do this, but you could also do it like this. And divide that number by 5, and wow, look at that! You get the same exact number. Surprise! It doesn't matter which one you use. I did both just for completion, but you don't have to do both. They're in fact the same thing. So, those are just multiple ways to solve the same kind of question. So anyway, I hope this was helpful at some of the calculations. Usually they're plug and chug. You just have to pay attention to the context. So these were closed air columns. Closed end, so you need to do that. That's very, very important. Then, of course, the harmonic number with odd, the closed harmonic numbers are odd, so you have to just be careful with that. So either the visual versus the questions that you're being asked, take a look at those, and make sure that, of course, your centimeters is in meters and your algebra for this part. I hope this was helpful, and have a nice day.